Okay, so let's continue. So yeah, we are talking about some properties of being closed under linear combinations of a vector. Then I was about to write this span of some vectors. Okay, so you remember what the span is? So it's basically a set of a vector, although the number of vectors is usually infinite numbers, right? So if we think about the span of these three vectors, and then all the possible linear combinations of all these three vectors will be just included in this span, right? So, do you think span is if span is always satisfying this condition of closed under linear combination? Do you think it's always true, or is there any other case that the span cannot satisfy this condition? Basically, span will always satisfy this condition of being closed under linear combination, because the definition of the span itself is just the set of all the possible linear combinations of the those basis vectors. And then if you linearly combine these two, then let's just do the addition of these two. 2 and 2. Okay, and then this will be our new vector. And then let's imagine the linear combination of this vector and then maybe this vector. And the linear combination of these two should also be included in the span. Would it be true? Yes, because it's 1 times the first vector and the other, plus 1 times the second vector. Okay, and then suppose we are considering the linear combination of 2 times this vector and then 3 times this vector. And then it will be like it's this times 2 plus 3 times 2, 1, 0. Okay, so if we just manipulate this equation, and then it will be just 2, 2, right? And then plus. So it's always represented as the linear combination of these three vectors. Okay. So the span is actually one good example of a subspace. And actually, span will be your only example of the subspace. So I was trying. I wanted to think about other possibilities of being other than span. I mean, some other subset of the vectors that are not span, but that is satisfying this being closed under linear combination. But that actually not true. I mean, there is no such cases. So span will be your subspace. So you can just simply think of it, span, as the subspace that satisfies these conditions of closed under linear combination. Okay, so let's go back to the slide. And so I was talking about these two properties. So the book or this slide says it should satisfy these three conditions, and then these two can be replaced as a one single constraint or one single requirement of let's just read through them. So we have two vectors, and then addition should be, I mean this subset of the vectors should be closed under the addition of these two vectors, and also scalar multiple of a particular vector. And then if we combine these two, and then it can be written as this: C1 times U plus C2 times V, and then U and V will be the given vector or the any chosen vector from H. Okay, and then you guys know the span. So span of any vector will always include zero vector, because if we just simply use a linear combination coefficient as 0, 0, 0, and then we will always have the zero vector, right? So this first condition of containing always this zero vector in your subset, that will be also part of this condition, linear being closed under linear combination. Okay. Okay, and then let's think about one example. So suppose we are given these two vectors, v1 and v2, and this is a v1 and this is a v2. And then in order to be closed under linear combination, then your subspace or the subset of the vectors, yeah, it will be just a span of these two vectors, right? Okay, and then this is some counter example of not non-subspace. So let's imagine the set of vectors along this line. Okay, so this is a 2D space, and so suppose this one is 1, 0, and this one is maybe 0, 2. Okay, and then your set will be 0, 1, because that is the middle point. So this one will be in your set of the vectors represented or drawn by this line. Okay, in this case, is it closed under linear combinations, or is it closed under addition, vector addition, or scalar multiple of a vector? So this is clearly not closed under the vector addition. So we pick up these 2 points, and then the addition of these two vectors, or the vector sum, will be this point, right? And this point is not included or contained in the our subset of the vectors. So clearly this line is not subspace. And also it is not closed under this scalar multiple. So we pick up this point, and then we just stretch out by the factor of 2. Then this vector corresponding to this point is not included in this vector subset, and so this is not satisfying the requirement of subspace. Okay, and then let's think about the special case. So when thinking about R3, for example, and then what about the R3 itself? Is this a subspace, or this universe or the entire set satisfying the the condition of being closed under linear combination? So we collect any of the three-dimensional vectors, then we think about the entire set. Then it's obviously closed under linear combination, because if we pick up any of the two vectors and then do the linear combination of it, and then that will still be another three-dimensional vector. So if we think about this entire universe, then that is closed under the linear combination, and so it is one particular example of subspace. And so this is probably the biggest subspace. And then what about the smallest subspace? What about this guy? Your set, vector set, is just containing the zero vector. In this case, it's also closed under linear combination. Okay, so you pick up two vectors, but you have only one entry, So yeah, the linear combination of 0 vectors will still be 0 vectors. Okay, then now let's discuss the main subspace that we will learn today. So we will basically learn two types of a subspace, which is called which are the column space and the null space or kernel. So and these two subspace is related to a given matrix A. So here the situation is, coming back to just a typical scenario of linear system. So we are given the matrix A, okay, but not given the constant vector B. And so we are given this matrix A, and then the column space of this matrix A is simply the span of the columns of matrix A. So it's a quite simple example. So 1, 2, 3, and 3, 4, 5, 6, 7, 8, 1, 0, minus 1. So this is your matrix A. So this is just a coefficient matrix. And then we are studying the definition of this column space of an A, which is the span of these four vectors, sorry. 6, 7, 8, 10, 1, 0, minus 1. Okay, so this is the definition of a column space. Okay, and then in the beginning of the lecture, I mentioned that subspace is a subset. A subset in a particular universe set. So what is a universe in our case? It is R3, right? Okay, and then let's check or think about whether it's possible to call it as a subspace. Okay, subspace. Is it a subspace? Which means is it satisfying the property of being closed under linear combination? The answer is yes, because by definition, it is defined as just a span of a particular vector. Okay, so this is a column space of an A, the definition of column space of an A. Then the next concept is this null space. Null space. So null space is this one. In the case of null space, we think about the homogeneous linear system. So in the case of a homogeneous linear system, this is our homogeneous linear system. And then now we consider the subset of the vectors that contains all the possible solutions of our homogeneous linear system. So in homogeneous linear system, we already learned 0, 0, 0, 0 is contained or it's always one of our solution for homogeneous linear system, and this is called a trivial solution, right? Because that is satisfying this. And then in this case, suppose this one has no free variable, and then this will be your only solution for homogeneous linear system. So there is no non-trivial solution, right? So this one will be your null space, okay? Because this is the only solution. And then is it satisfying the condition of subspace, which is being closed under the linear combination? The answer is yes, because zero vector itself is a subspace satisfying the closed under a linear combination, right? Then what about the other cases where we have non-trivial solutions? Non-trivial solutions. Okay, in order to compute the non-trivial solution, we have to change it to reduced echelon form, right? And then I'm gonna give you just a reduced echelon form as an example. So suppose this is your reduced echelon form of the original matrix A. Okay. In this case, you guys know how to represent your solution set as a parametric vector form. Then that parametric vector form is x1. Let's just is what? -1, then -2, then what? 1 and 0 times x3. So this was your parametric vector form. Okay. In this case, the entire solution set has the form of this, where you can freely change your parameter. Okay. Then what about having two vectors? So I simply change it as this guy as let's see. Let me change it as 0 and maybe 3. Okay. So is this echelon form? Reduced echelon form? Huh? No? Why? So we have, let's think about the pivot. So these are the two pivots. And then up and bottom, we see all zeros. And then we don't have any other pivots here. So it is still reduced echelon form. Then let's think about this parametric vector form. Okay, in this case, what is our parametric vector form? -1, -2, and 1, 0 times x3 plus what? What is the second vector? So we see two free variables, x3 and x4. What is the vector? 0? Can anyone give a clear answer for it? 0 and -3. Yes. Right. You guys know how to obtain this, right? So this is just nothing but the the obtaining a parametric vector form from a homogeneous linear system. Okay. So in this case, 네. 네. x4가 왜요? x4가 네. 이거 리듀스 에실론 폼이 아니에요?
그 열에서 피봇 진 열에서는 피봇이 우리 하나의 영이 아닌
맞아요. 이 초록색으로 내가 표시한 게 피벗이죠. 그리고 위아래 다 0이고요. 그 다음엔 또 피벗이 있나 보니까 없죠. 네, 그거를 0으로 지금 바꿨어요. 네. Okay, so yeah. Sorry about the confusion. So I'm talking about the different example where we removed the pivot here as 0. So we now consider the second case where we only have 2 pivots. Okay? So in this case, this is our solution set. Okay? And then the question is, yes, because we are studying a subspace, is it a subspace? Or, in other words, is it satisfying the condition of being closed under linear combinations? Or, let me change it to a simpler question. Is it a kind of a span of a particular vector? Is it span or not? So these two are free variable, right? So you can freely choose. And then, as it is, this has the form of a linear combination of these two vectors, right? And so this one can be represented as span of -1, -2, 1, 0, then 0, -3, 0, 1, right? So this is a span, right? Using your vectors that you obtained from factoring out the homogeneous linear system solution, right? So this is a span, and so this is also closed under linear combination. Okay, and then this guy or this guy, or whether you have a free variable or not, the solution for homogeneous linear system of a particular vector, a particular matrix A, again, the solution of a homogeneous linear system is also a subspace, and that subspace is called a null space. So we just give a special name for it as a null space. And then in the case of, let's see, yeah, the linear combinations of these columns of matrix A, we call that as a column space. So these are the two special subspace that we learned today. Okay. Okay, and then yeah, although it's quite obvious, let's think about their entire set. So we basically talk about subspace, which is a kind of subset, and then what is our entire universe. In the case of column space, this is part of R3, but in this case, the null space is part of R4, right? Okay, so column space and null space will have will be from, they are living in the different space. So we are living in 3-dimensional space, but some other, like aliens, they are living in like a 4-dimensional space. Okay, so the entire space is totally different between these two. But they have some interesting relationship, as we will see in later in today's class or the next class. And yeah, so in order to study that, let's study the new notion of basis. So the basis. Okay, basis is, you can think of it. You can think of basis as a like the smallest possible set of the vectors that will form the same span. Okay, so yeah, let me give a intuitive explanation. So we have these two vectors in the three-dimensional space. So span is exactly the same as subspace. So you can think of it that way. And then the span of these two vectors will be this plane. And then what about being given three vectors? But they are linearly dependent. And so in this case, their span will still be this plane. So in this case, the span, let me ask the question. Let's think about the two different spans. So the first span is using these three vectors, and then the other span is just removing this guy, and then using these two vectors, and then span them. Are these two subspace the same or not? So, it is just the same because this is just a redundant vector. Okay. So, when thinking about this column space or this null space, we are given the ingredient vectors, such as this guy and this guy, or this guy, this guy, this guy, this guy. Okay? So from those ingredient vector that will form our span, we want to just remove redundancies. Okay? We just want to remove the redundancies, which means if one vector can be represented as a linear combination of the other vectors, and then it doesn't matter whether we remove it, right? So that we have the same span, right? So suppose we removed some redundant vector, or suppose we removed all the possible redundant vectors, and then the remaining vectors will be always linearly independent. Okay, linearly independent. So given your subspace, so again I mentioned that the subspace is the same as a span of some vectors. Okay, and then given those vectors, if those vectors are spanning your subset, okay, and then these are also linearly independent, which means you basically remove the redundancies. So within this smallest possible set of vectors, there is no redundancies, which means there is no linearly dependent columns or vectors because we removed it. And that compact ingredient vector that will span our subspace, that is called a basis. Okay, that is called a basis. Okay, so let's look at the definition of the basis. So basis for a subspace H. So we don't know the details of a particular subspace because we are not given the details of it, but this basis, the definition of the basis for this subspace means this basis has to span the entire the given subspace, and also they have to be linearly independent. Okay. Okay, and then let's think about the special case or simple case of an invariable matrix. So invariable matrix means we are considering the square matrix, and then from the invariable matrix theorem, we learned that all the columns are linearly independent, right? So the first and the second and the third vectors are linearly independent. And then if we think about the column space of A, so this is written as this. So column space of an A is the span of these three vectors. So let's call that as A1, A2, A3 as a vector. Then A1, A2, A3 as an ingredient vector. And then they are linearly independent. And why? Why are they linearly independent? So if you remember all the different items or entries in the invertible matrix theorem, and then it has, if it is an invertible matrix, and then its reduced echelon form will be just the identity matrix, right? Identity matrix. And then it means all the three columns are linearly independent, and so when thinking about adding one vector at a time, so we start with this vector first, and then the second vector, and then the third vector. Any vectors are not inside of the span of the previous vectors. So always the new vector or newly added vector will always give you, will always expand your space. Okay, and so in this case they are linearly independent, and at the same time they will span the column space, right? I mean the span of them will be the same as column space. So they can be called a basis because the column space is spanned by these three vectors, and then all the three are always linearly independent. And so we can call them safely as a basis of this subspace. Okay, and then let's think about how big this space is. So let's think about the entire subspace, entire space or our universe where these vectors are living in. So if we are thinking about the three-dimensional vectors, then the entire universe is R3. So in this case, the span of these three vectors will span the entire universe. Is it true? In the case of an invertible matrix. So if you recall or remember the invertible matrix theorem, this matrix A should always row reduced as an identity matrix, which means every row and every column is every column has a pivot, and every row has also a pivot. And then the fact that we have a pivot in every row means the span of our columns, or the linear combination of the columns of an A, will completely cover up the entire space. So that's why we always have a solution for any vector B, right? Okay, so these three vectors are actually spanning, or the span of these three vectors will become the entire universe. Okay, so let me just re-emphasize these two things. So in the case of invertible matrix, so if it was a 3 by 3 matrix, or let's think about the 5 by 5 matrix, and then of course we will have a 5 columns. And then the span of these 5 columns will have the basis as the same as the same set of 5 columns, which means the 5 columns are always linearly independent, so they will become the basis for this subspace of a column space, right? So they will automatically become a basis, and also the subspace itself will be just the entire universe. For example, R5 in this case. Okay, and then let's think about some other case where the ingredient vector are not actually your basis. So what I mean is, so let's think about this matrix B, and I don't know why, but we already have the reduced echelon form. So we are just thinking about the simpler case of reduced echelon form. So if your matrix is this reduced echelon form, then let's think about the span of the 5 vectors, or the column space of B. Column space of B will be the same as span of 1, 0, 0, 0, and then 0, 1, 0, 0, and minus 3, 2, 0, 0. I'm just rewriting it, this matrix. column by column. Okay, so this is your column space, and then what is the basis for this span or the column space? So the question is, are all five vectors our basis? So we can remove some of them because some of them are linearly dependent, right? So which one can we remove them? Right, the third and the fourth. Okay, so your basis is actually only the three vectors after removing the third and the fourth vector here. Okay, and then can we show this vector is really linearly dependent, or is this vector really represented as a linear combination of the previous vectors? So for example, we are given these two vectors first, and then the third vector is inside of the span of the previous vectors. Is it true for free variable? Or in this particular example, is this the third vector a linear combination of the previous vectors? Is it true? No? Why do you think it's not true?
So 1 and 2 and 5 are linear combination.
They are linearly independent.
And linear combination because they span.
Uh-huh. Okay, so let me ask the question more clearly. Is this a vector? Yeah, can you represent this vector as a linear combination of the previous two? Which means these vectors. Or using these two vectors, can you represent the third vectors? And then what would be the linear combination coefficient of B1 and B2? Yeah, it's a minus 3. Then it's right? Why? So you can just construct this minus 3 using this first pivot. Okay? And then that way we have minus 3 times B1. And then using this second pivot, you can just reconstruct the 2, right? And so this is your linear combination of representing B3 as by using the previous 2. Okay? So that way we confirm that B3 is a linearly dependent. Okay? And so we remove them, and then we can do the same thing. What about B4? So we have this vector, and so 5 here, and so simply B1 times 5, and then minus 1 times B2. So that way we can represent the fourth vector as a linear combination of the previous vectors. Okay? So once we remove them, and then span will remain the same. Okay? And then they are linearly independent, and so we can now call them as bases. So this sentence is really important. So this is a kind of useful fact that you can utilize probably in your homework. So the columns that contains the pivot. So those vectors will form your basis for the column space of an A. Okay, and then let's look at the next question. So the next question is, it's a little bit, there is a typo. So yeah, it is saying that it can be verified that this matrix A will be row reduced B, which means we have B here. So this matrix, if you do the row reduction, and then you will obtain this matrix. Okay, so this is one example of one matrix that has the row reduction form or reduced echelon form of this. Okay, and then in this case, we know the pivots are contained here, here, and here, and the the third and the fourth variables were free variable, right? And then in this case, what is the basis of the column space? What is the basis of a column space? So span, we are talking about the ingredient vector that will span our subspace. Then it will be 1 minus 2, 3. I'm just writing it again for those 3 vectors, and they are linearly independent. And then let me also ask the question. So just almost the same question. So let's think about this column. Can we represent this column as a linear combination of the previous two? And then what is that representation? So again, A3 is some number times A1, and then some number times A2. So what is the linear combination coefficient? So it is a little bit tricky, right? It's not revealed, right? But here the important thing is, so once you obtain this row reduced echelon form, and then you obtained this relationship, okay? And then let me just give an answer. So you can simply bring those two coefficients, then put these coefficients as in the same place here. So in this case, this relationship will be also true. And why should it be true? So if matrix A and B has the same, so they are like a row equivalent, which means you row reduced A to B, and then do they change the solution set at all? For example, so suppose you have 1, 2, 3, 4, 5, 6. So this is your A, and then this is a this has an echelon form of this. So this is clearly not true, but let's assume that A is row reduced as B. In this case, AX equals 0, then BX equals 0. Let's think about the homogeneous linear system of each matrix, and then the solution will not change, right? So that's why we can do the row reduction to obtain the solution of the original system, right? The solution is not changing. Okay. So in this case, we constructed this equation of B3 is minus 3B1 plus B2B2. Is it true? Okay, yeah. So in this case, this linear combination relationship can be viewed as this. Minus 3 times B1 plus 2 B2 plus minus B3. And then if we had a more example, so more columns, B4, 0 times B5 equals 0, right? So I just simply moved to here, moved this guy to the right, and then just assign the 0 linear combination coefficient on the vectors on the right that we haven't used yet. Okay. So suddenly this will become one non-trivial solution for your homogeneous linear system. So again, we started from here, and then we changed it to this equation, okay? And then this one will become B1, B2, B3, B4, B5. Then what is your solution in this case? It is minus 3, 2, minus 1, 0, 0. Okay? So that way, this one equation that you easily constructed by using this guy to this guy and this guy to this guy, right? So that way you easily obtain this equation, but that is actually one non-trivial solution for your homogeneous linear system, because we can change it into this and this. Okay, and then this homogeneous linear, the solution for this homogeneous linear system will be also the solution for this homogeneous linear system, right? And so the same vector will be your solution, and then the same equation will also be true, and then this equation will also be true. But here, instead of using B's, we can now use A, the columns of an A, right? So we basically change all B1 through B5 and those columns as A1 through A5. Okay? So, so back to this example. Now we can understand why this guy is true, right? Because we simply change it this equation that we obtained from its reduced echelon form, and then we can change all the B columns as columns of A. Okay, and then you can verify if that is true. Okay, so you can just plug A, B, and so on into this equation. Okay, then I think you guys are smart enough of not being confused about this fact, but this warning, I mean this paragraph is saying that so even though you pick up the pivot columns as your basis, okay, again the pivot columns will become your basis for column space of an A, right? But you have to pick up those columns from your original matrix, not from your reduced echelon form matrix. Okay, so one mistake is, let's imagine you are taking the second midterm exam, and probably this problem might be actually appearing in your exam. So find your basis of column space of this matrix, and then you will do the row reduction of it, and then find out which variables are pivot variable and then which ones are free variables, right? And then you identified from the location of the pivot, third and the fourth columns are free variable or non-pivot columns, and so you have to pick up the first and second and fifth, but you have to pick up those columns not from this reduced echelon form matrix, but from your original matrix, right? And then it can be understood clearly if you think about this example. So if once you change your matrix into this echelon form, reduced echelon form, this reduced echelon form will have all these zeros, right? So if you picked up the first, second, and fifth, and the fifth dimension will always be 0. So even if you linearly combine them, the span of these three columns will always have zeros at the last entry, right? But what about this case? So let's think about just all the possible linear combination of these columns. So if we just pick up the first column by just a linear combination, by using the linear combination coefficient as 1, 0, 0, 0, 0, in this case, it already has some non-zero entries here, right? So this vector is not represented by the linear combination of these three vectors in your reduced echelon form. So you shouldn't pick up the columns from your reduced echelon form. Your reduced echelon form will only tell you which columns to choose. And then those columns should be picked up from your original matrix A. Okay, so that's it for chapter 2.8. Then let's do a little, study a little bit on the next chapter. But it's really in the continuation of, it's really built on top of the previous one, so it should be easy, hopefully, yeah. Okay, then, let's do a little bit, informal kind of, ways. So since we discussed basis of a particular particular subspace, so we have a subspace and then their basis. Okay, and then the question is, for the same subspace, would the basis be unique or not? The question is whether the basis is unique or not. Not. Why? Why? So the question is, so I'm gonna use my finger again. So let's use these two as our basis. Are they linearly independent? Yes, because they are not along one line. So if you think about two vectors, and then if they are not along one line, one single line, and then they are linearly independent, then the span will be this plane. And so those two vectors and set of these two vectors will be your basis for this subspace. Then what about other basis? So how about picking up the two vectors from this plane as this, for example. So I'm gonna just change the angles as well, and then maybe the length of the vector. Okay, so like this, or a larger vector. Okay, that will span the exact same space.